This is a force example problem, finding elevator acceleration. Here's the problem we're going to be looking at. A 1,600 kilogram elevator is suspended by a cable under 19,000 newtons of tension. The elevator has no other support. What is the acceleration of the elevator? I'm going to begin by picturing this scenario. There's an elevator and it's held up by nothing other than a cable. And so if I draw a boundary around this elevator and imagine the forces acting on it, anything crossing through the boundary, there's definitely a force acting. And so there's a force acting here. That's the tension in the cable. And we're assuming this is happening on Earth, and so there is weight pointed down towards the center of Earth. The problem doesn't give me any information about the motion of the elevator. I don't know if it's moving up or moving down or stopped. It asks about the acceleration. So at this point I need to recognize that Newton's first law of motion says that a force is required to produce an acceleration. This is going to be a problem about finding that net force, which is responsible for the acceleration. I also need to keep in mind Newton's second law, which tells us that the sum of forces is going to be equal to the object's mass times its acceleration. So once I can find the sum of the forces acting on this elevator, I should be able to solve for the acceleration, particularly since I've been given the mass. I am at the point where I am going to draw a free body diagram. So there's a dot which represents the elevator. There's a weight pointed downwards and a tension pointed upwards. I can set aside an area for side work if I want. This is where I can kind of make notes, do unit conversions, those sorts of things, and I can copy over some of the information that I was given. So I was told that the mass is 1,600 kilograms. Now I know that weight is not the same thing as mass. Weight is equal to the gravitational force, so mass times the gravitational acceleration, mg. And so that means that weight is equal to, I kind of have to skip on to another line here, 1,600 kilograms times 9.8 meters per second squared. So weight in this problem turns out to be equal to 15,680 newtons. The question also told me that the tension in the cable is equal to 19,000 newtons. Alright, so these things are going to be useful as I set up my table of forces. I'm going to write down every force in the problem, so that's tension and weight. It's not a big list. And then I'm going to write down the x components of those forces. Well, I can just look at the picture and I know that there's nothing acting in the horizontal direction. So here's my coordinate system. I've got x and I've got y. Nothing is acting in the x direction. The y direction, though, that's where everything's happening. So the component of tension in the y direction is a positive 19,000 newtons. It's positive because it's pointed up, which on my coordinate system is a positive y direction. Weight is pointed down. On my coordinate system, that's a negative y direction, and so that's a negative 15,680 newtons. So then my next step is to add everything up to get the sum of forces. The sum of the forces in the x direction, that's 0. The sum of the forces in the y direction, let me draw a line to kind of separate this out because it's going to be tight. That's going to be 19,000 minus 15,680. And so the sum of the y forces is going to be equal to 3,320 newtons. Now I'm not quite done. I need to set that sum of the forces in the y direction, that's my net force, equal to the mass of the object times its acceleration in the y direction. So 3,320 newtons is going to be equal to 1,600 kilograms times this acceleration. Now I can double check with the problem to figure out what I was asked to solve, but this one was fairly straightforward. So I remember I was asked to solve for the acceleration, so we're just about there. So I'm going to divide both sides here by a 1,600 and what I get in the end is that the overall acceleration is 2.1 meters per second squared. And this is my answer. Put a box around it.